In my last video, I looked at railguns. Now, whilst I was reviewing the footage, I started wondering how they filmed the projectiles in flight. These are not the typical sort of high-speed camera shots where you see a bullet hitting a target, for example. These are tracking the projectile from the barrel down the firing range. From the footage, it looks like the camera is panning around and following the projectile, but that would be impossible. The tank round is travelling at over 1,500 meters per second and would normally look like this. For all of you out there who said it's done with mirrors, then you are absolutely correct. It works by having a computer-controlled high-speed rotating mirror in line of sight of a high-speed camera. The speed of the rotation of a mirror matches that of the object being followed, so the faster the object is travelling, like a railgun projectile, the faster the mirror would turn to keep up with it. Using this method, the object can be kept in the field of view for 100 meters or so, or about 90 degrees of the mirror's movement. In this example, the Tracker 2 from Specialized Imaging, you can see the mirror and to its left where the camera is. Because the mirror is computer controlled, it can be programmed to follow objects that accelerate either linearly or non-linearly. Now, rotating mirrors aren't new. In fact, they were some of the first high-speed cameras and are still some of the fastest in the world, capable of up to 25 million frames per second, and were used to record atom bomb blasts. During the Manhattan Project to develop the first atomic bomb, they required cameras that could record the first few microseconds of the explosion. In order to create a nuclear chain reaction and achieve critical mass, a baseball-sized piece of plutonium had to be compressed to about half its size. This was achieved by using an array of focused high-explosive lenses surrounding the plutonium core. In order to make it work effectively, the explosives, 32 of them in all, had to be triggered within 1 microsecond. If any were delayed, then the compression of the core would be unequal, and the reaction would either be much less or may not even happen at all. Using a super high-speed camera, it would be possible to see how effective the explosive lenses had been just a few microseconds after detonation. At the time, the fastest cameras were Fast-Tax Cine cameras and could achieve around 10,000 frames per second, or 1 frame per 100 microseconds. This still wasn't fast enough though. The first high-speed rotating mirror camera was the Marley, invented by the British physicist William Gregory Marley. The Marley camera used a rotating mirror and an array of lenses inside a curved housing, each focused onto a single piece of film around the edge of the case. This could record a sequence of up to 50 images onto 35mm film at 100,000 frames per second. But by the time of the Trinity test, it was outdated and too slow to record the ultra-quick reaction in the plutonium core. Head of the photography unit, Julian Mack, said that the fixed short focus and low quality of the lenses would probably have made the Marley camera pictures useless. He helped develop the Mack Streak camera, which had a 10 million frame per second limit. That's 1 frame every 100 nanoseconds. By the 1950s, Harold Egerton had developed the Rapatronic camera, the name coming from Rapid Action Electronic. This used a magneto-optic shutter, which allowed it to have an exposure time as short as 10 nanoseconds. That's 10 billionths of a second. This was first used for the hydrogen bomb test of the Eniwetok Atoll in 1952. However, they only took 1 image. So to see the first few microseconds of a nuclear detonation, up to 10 were used in sequence with an average exposure time of 3 microseconds. The images were then played back and blended together to give the impression of a film. For the British nuclear tests, the Atomic Weapons Research Establishment created the C4, a huge rotating mirror camera weighing in at around 2,000 kilograms and was the fastest in the world at the time. This could record up to 7 million frames per second, with the mirror rotating at up to 300,000 revolutions per minute, and recorded the first British atom bomb test on the 3rd of October 1952. The rotating mirror cameras are still in use today, but now they use highly sensitive CCDs to replace the film strip. The Brandar S128 and Cordin Model 510 have 128 CCDs and a gas-driven turbine mirror driven by helium to achieve up to 25 million frames per second at a resolution of 500 by 292 pixels for the Brandaris and 616 by 920 pixels for the Cordian. At 25 million frames per second, the mirror itself is running at 1.2 million revolutions per minute. That's 20,000 revolutions per second. So fast that the atmosphere inside the camera is 98% helium to reduce the friction and the pressure waves that would occur in normal air. And so on to something I think you may find rather interesting. It's not the fastest camera in the world, but this one is, or it was at the time in 2013, the fastest real-time tracker of a moving object and was developed by the Ishikawa Oku lab at the University of Tokyo. Here it is tracking a ping pong ball and keeping it in the centre of the frame at all times, both during a game and when it is being spun around on a piece of string. It does this by moving two mirrors in front of the camera, one for the X movement and the other one for the Y movement. It then uses software similar to face tracking software to provide feedback to control the mirrors with a response time of just 1 millisecond. It can also be used to control a projector, and in this scene it's projecting an image onto the ping pong ball whilst it's being bounced on the mat. You can see the little face change on the ball at the top of its travel. Anyways, I hope you enjoyed this look at some of the equipment behind some of the most amazing footage recorded to date. These aren't the fastest cameras in the world now, but it's still amazing to think what can be achieved by mechanical means. So as always, thanks for watching, and don't forget we also have the Curious Droid Facebook page, and I would also like to thank all of our patrons for their ongoing support. And if you would like to support us, then you can find out more on the link now showing. So thanks again for watching, and please subscribe, rate and share.